Welcome, one and all. We are now at the stage where we can introduce limits, and in this video we will spend some time discussing a numerical approach to limits. At the base of all calculus is the notion of limits. We're going to discuss how a function can be defined at a given point and yet have no limit, and vice versa. In rough terms, let us define what it means for x to approach a. We write x heading towards a superscript minus to represent the left-hand approach. That is, values given to x are getting closer and closer to a while remaining less than a itself. X heading towards a minus is red. X approaches a from the left. For example, here is a sequence of numbers where x is approaching 2 from the left. Which is also true about the following sequence, where x values are still approaching 2 from the left, despite being different set of values from what we saw previously. Graphically, we can think of successive values approaching 2, but remaining left of 2 at all times. Likewise, the right-hand approach, written as x heading towards a plus, represents the fact that values given to x are getting closer and closer to a while remaining greater than a itself. X heading towards a plus is red. X approaches a from the right. For example, this shows a sequence of values where x is heading towards 2 from the right. And in the same manner, here is a different sequence of values where x approaches 2 from the right. Again, graphically, you can think of sequentially picking values of x that bring you closer and closer to 2 while remaining to the right of it. The notation x heading towards a is used to represent all arbitrary ways with which x approaches a. Amongst these approaches, there is the left-hand approach, the right-hand approach, as described previously, as well as all other ways of approaching a. For example, these two approaches are not one-sided approaches, but yet x is systematically getting closer to 2. The first sequence of numbers alternates between numbers that are to the left of 2 and to the right of 2, yet getting closer. In the second sequence of numbers, we are to the right of 2 at first, and then all of a sudden to the left of 2, but still getting closer to it. Both examples satisfy the notion conveyed when we write x heading towards 2. In this case, sequences of values have to simply get closer to 2, regardless of how that takes place. Observe that in all cases shown previously, although x inches its way towards a, it actually never takes that specific value. The limit of a function is a bit more abstract than is the case of a limit as x approaches a, because now two variations are going to be taking place simultaneously. As we allow x to tend towards a, as we've shown previously in some of our sequences, we are also observing the effect that this approach has on the value of f of x, that is, on the y value that results from our choices. In terms of notation, the limit as x approaches a minus f of x is meant to evaluate the value of the function f of x as we let x approach a from the left. For example, let's evaluate the limit of function f of x as x approaches 2 from the left, given that f of x is 9x over x squared plus 2. Again, remember that x approaching 2 minus means that x is approaching 2 from the left only. As we saw earlier, such an approach can be constructed with a sequence such as the following. So here are sequences of numbers that are approaching 2 from the left. Then we replace x by this sequence of numbers into the function that we defined as f of x equal 9x over x squared plus x. Now observe how the values of f of x are approaching 3. So it appears that the effect resulting from x going towards 2 minus is that 9x over x squared plus x is heading towards 3. Assuming that our deduction is accurate, we could write that the limit as x approaches 2 from the left of 9x over x squared plus x is equal to 3. Or the limit as x approaches 2 from the left of the function we denoted as f of x is equal to 3. Graphically, we can visualize the limit process by, again, looking at values of x that are heading towards 2. And here's what's taking place. And as those values of x are heading towards 2, notice how values of y are becoming closer and closer to 3. Similarly, writing the limit as x goes towards a plus, or x heading towards a from the right, of f of x is meant to evaluate the value of the function as we let x approach a from the right. For example, let's evaluate the limit for the function f of x as x heads towards 2 from the right, given that f of x is once again 9x over x squared plus x. Once more, we're going to keep in mind that as x heads towards 2 plus, it means that we are letting x approach 2 from the right only. So, as a first step, we've constructed a sequence of values of x that are approaching 2 from the right. Then, we can evaluate the function's value at all of these sets of numbers. Notice how the function's values are approaching 3 as well. So it appears that the effect resulting from x heading towards 2 from the right is that 9x over x squared plus x is heading towards 3. So again, assuming that we are making the right implications here, we can write that the limit as x heads towards 2 from the right for the function 9x over x squared plus x is equal to 3. Or that the limit as x heads towards 2 from the right of our function called f of x is equal to 3. We can visualize the process that just took place. So this time I started off with an x value of 3, and I will systematically choose values of x that are getting closer to 2 while remaining to its right. At the same time, observe how y components of these dots are becoming closer and closer to 3. When we merge the two approaches, it seems clear that the direction with which x approaches 2 has no influence on the outcome, which is that f of x tends towards 3 as x approaches 2. Given that both the left hand and the right hand limits as x approach 2 both agree on producing an outcome of 3, we can then also state that the limit as x approaches 2 with no mention of the directional approach for the function 9x over x squared plus x is equal to 3. This basically means that regardless of how we head towards 2, 3 will be the limiting value of the function. Some of you may already be wondering at this time why we simply just didn't calculate f at 2 directly, since 9 times 2 over 2 squared plus 2 would have given 3, rather than going through the tedious process of computing left and right hand approaches. This is a subject we'll have to discuss in our next video.